Hello, my name is Matthew Zerba. I'm a master's degree student at the University of Michigan studying aerospace engineering. And I'm here today on behalf of the University of Michigan and the Michigan Exploration Laboratory to talk to you about expanding the capacity of satellite operations using a global federated ground station network. Small space programs like those at academic institutions and at startup companies are limited in their operational resources. These include monetary budget, time, and ground hardware. Setting up new ground stations can be difficult and expensive for these small teams, and operating additional ground stations offers some key benefits. In addition, ground stations operated by a single entity for just a few spacecraft experience a lot of downtime, and this is a kind of an inefficient use of this specialized hardware. One potential solution for these problems is the use of a federated ground station network, or FGN. These provide access to diverse station locations and RF hardware, as well as greater contact time, data throughput, and scheduling flexibility. The Michigan Exploration Laboratory, or MXL, has used the Satellite Networked Open Ground Station Project, or SATNOGS, for operating some of its CubeSats. SATNOGS has provided MXL's TVEX mission with some critical operational advantages, including the identification of a spacecraft malfunction immediately after deployment, a 6 to 16 times expansion of weekly downlink contact time, and a 2.2 times expansion of real-time beacon collection. SATNOG's open model also prompts some worthwhile questions for the community to consider about the future of FGNs. Small spaceflight programs have become more and more common in recent years, especially with the advent of the CubeSat. By the end of 2018, we've tracked 192 academic programs, flying a total of 428 missions. 55% of these programs have only flown one mission. Again, small satellite programs face some operational challenges, including budget and resource constraints, and limited team size and limited team experience. The lack of access to multiple ground stations also limits the orbital profiles available for missions, comlink availability and efficiency, and real-time awareness of spacecraft state of health. Now, what is an FGN? An FGN is a loose collection of ground stations connected to a network. In our case, this network is the internet. Stations and their hardware are owned by different parties individually. Owners can add and remove their stations from the network at will, and stations can be operated remotely and autonomously by its users. Data capacity models have been developed to analyze the performance of FGNs. Two parameters that I think are important for us to analyze are link efficiency and link availability. Some other advantages of using an FGN are improved hardware diversity, different antennas and the like, higher station utilization rates, which decreases that inefficiency I was talking about, and more frequent spacecraft health checks. Some past FGNs include the Mercury Project and GENSO, which is the Global Educational Network for Satellite Operations, managed by the European Space Agency. SATNOGS is a modern FGN example. It was founded in 2014 by the Libre Space Foundation and is open source. As of the 30th of June 2020, it had 235 active ground stations worldwide. These stations can run on something as simple as a Raspberry Pi, given that you have an antenna and a simple software-defined radio module. And SATNOGS has an integrated data analytics dashboard called Grafana, which allows you to visualize and analyze your data that you've collected over the network very easily. Any member of SATNOGS with a participating station can schedule observations of satellites, and the built-in scheduler makes observing these satellites very easy. On the right here is a picture of two MXL members with all the hardware they need for a SATNOGS station. Here's a map of where all the SATNOGS stations are located as of May 2020. And the green dots are the active stations, and the orange dots are stations that are on the SATNOGS network but are currently in test mode. As you can see, a lot of the stations are clustered in North America and in Europe, but there are stations on all 6 populated continents, which helps with that link availability. MXL uses SATNOGS to observe some of its already orbiting CubeSats. Most notably, we have the Tandem Beacon experiment on the left, which is a pair of 3U CubeSats, Griffix in the center, which is a single 3U CubeSat, and MCube2, which is a single 1U CubeSat. Packets from SATNOGS and the MXL stations are combined using the MXL Integrated Data Analysis System, or MIDAS. This is an in-house database developed by one of our student researchers. MIDAS allows operators to access data through APIs and GUIs, which makes it easy on the operations teams to analyze their data. To show a real-world example of the use of an FGN like SatNOGs, we're going to look at the example of the Tandem Beacon Experiment, or TBEX, shown on the left here. Some background for TBEX. TBEX is a recent MXL mission. It's a set of 2 identical 3U CubeSats funded by NASA and SRI International. They're tasked with investigating ionospheric phenomena like the structure and evolution of plasma bubbles in the upper atmosphere. And they were launched a little over a year ago on June 25th, 2019. The mission requires a configuration that was a new challenge for MXL, especially its low inclination orbit of 28.5 degrees. Its altitude is also low, with a 300 kilometer perigee and an 850 kilometer apogee. On top of all this, they have to be nadir pointing. MXL's home ground station is in Ann Arbor, Michigan, at 42.29 degrees north latitude. This is quite a bit higher than the inclination of the orbit, which makes it hard to have long contact times with the spacecraft. MXL's home ground station is situated at the François-Xavier Bagnoud Building, or FXB. On the right, you can see that same picture from before, the TBEX satellites, a little bit larger. So right after deployment of the TBEX satellites, we immediately saw the benefit of using SatNOGs. On deployment, both TBEX satellites experienced some radio instabilities that prevented them from contacting the FXB at all. And the FXB is the only location that we can uplink data from. SatNOGs improved the TBEX link availability, which allowed TBEX to be observed in other locations at other times. These observations provided some critical information, such as the fact that the satellites were still functional and not just dead on arrival. And the radio signals collected allowed us to tune the ground station radio hardware we have at the FXB so that we could recover communications with the spacecraft. After all that drama, we were also able to have an easier time pairing the TLEs of our spacecraft with the JSPOC identification numbers due to this early identification of our spacecraft. We had a SatNOGs user named Freddie Demkalis help us with some of these early observations. On the right here, you can see a waterfall plot that shows our radios malfunctioning in the early days. So one of those 2 parameters that I want to talk about is link availability, which is a measure of how much time a network can connect with the spacecraft. The FXB station alone can contact the spacecraft about 1 to 4% of the time, depending on which week you measure it. Now, the FXB station is located 13.8 degrees above the TBEX orbit inclination, and which limits the amount of time that we can contact it. Also, since TBEX A and B's orbits are so similar, only TBEX B data will be shown here for brevity. If you want to see how close those orbits actually are, there's some TLE plots in the backup slides. On the right here, we've got a plot of link availability per week in a 4-month span from October 2019 to February 2020. As you can see, it varies between 2 and 6 hours per week, which is, as I said, 1 to 4% temporal coverage. This data was generated using an STK simulation informed by real-life TLEs. Now you can see this large variation has similar period to the period of the argument of perigee. These are actually measured TLEs of the 2 spacecraft here at the left. And as a matter of fact, this precession of the argument of perigee is actually the driving factor behind this large variation in the amount of contact time, since lower in altitude of the spacecraft passes have less time where we can see the spacecraft. So what happens to the link availability if we add some SatNOG stations into the mix? Here you can see the location of 6 SatNOG stations in addition to the MXL home station at the FXB. I plotted the locations of these stations because these were the stations that we used most often over the past year. They collected 96.4 of all unique TBEX beacons. That's true of these SatNOG stations plus the FXB. All right, so I made a similar plot here on the right. You can see the cyan link availability bars, the same as a couple slides ago. And on top of that are the marginal link availability times that you gain by adding additional SatNOG stations. Now, these are the same stations shown on the previous slide, but you'll notice there are only 4 colors, and that's because some of the SatNOG stations are very near to one another, and they completely eclipse each other in contact time. So these were plotted from bottom to top in order of increasing geographical distance. So you've got the cyan your experimental control here, our home station. You add in station number 50 from SatNogs, you get this red amount of time. You add in station 623, you get this amount of time, and so on. And of course, by adding additional stations, you can get even more time. So this has increased, just these 6 stations adding onto the FXB has increased our link availability by a factor of 6 to 16, depending on when you measure it. That's an increase of temporal coverage of 1 to 4%, up to 18 to 21%, which is pretty good. Another way to measure the performance of an FGN is to look at data throughput. And so I am showing you here some data about beacons that we've collected from the spacecraft. Over that same 4-month span of time, from the 7th of October 2019 to the 3rd of February 2020, we collected 26,667 unique beacons from both TBEX satellites. 20 SatNog stations were involved in the collection of these beacons, and just 6 of those stations accounted for 93% of the SatNog's only beacon collections. And those 6 stations are the ones that I've shown before and have plotted here. In this plot at right, beacons were only attributed to SatNog stations if they were not also received at the FXB station. This plotting decision was made to show the growth in data throughput that we get by adding SatNog stations. And also duplicate receptions at SatNog stations were distributed in even fractions across the receiving stations. Looking at this plot more carefully, you can see that we more than doubled the amount of beacons that were recovered by the use of the SatNog stations compared to what we received if we had used the FXB alone. In the future, MXL plans to use SatNogs to downlink large files. An example of one of these large files is the history of all the beacons. So every 10 seconds, TBEX generates a beacon. Each satellite does. These beacons are 410 bytes and are spread across 2 AX25 packets and transmitted to the ground. They're also stored on board the spacecraft, and because a lot of those transmitted beacons don't make it into our database, we would like to have access to those to do some data analysis on the long-term health evolution of our spacecraft. Other MXL CubeSats have similarly sized beacons, by the way. Doing some multiplication, you can see that these beacon logs will grow by about 3.5 megabytes per day uncompressed, and MXL is working on downloading this data en masse. Downlinking over SatNog stations increases data capacity by increasing both the link availability and the link efficiency. Link efficiency is the measure of how many transmitted packets are received. Downlinking over the home ground station also decreases the amount of time for commanding. We only uplink to the spacecraft from the FXB, so if we could downlink over other stations, that would free up some time for us for commanding. Recently, MXL has developed the ability to schedule satellites to autonomously dump data over these stations as well. All right, lastly, I want to talk about some future considerations for FGN technology. SatNog is a modern example, but FGNs are still a young technology, and choices made in the early stages of a technology can shape the future of that technology. SatNog's existence highlights 3 points that we think are worthwhile for the community to consider. One is how to fairly and efficiently allocate network resources when observation demand exceeds ground resource supply. Right now, there is far more supply in the SatNog's network than there is demand for it, but that may change in the future if the technology continues to become more popular. Second is how to protect the priority of station owners over their own station's time. So if I have a ground station that I'm using for my satellite, and I'm also willing to share this capacity with the community, I need to make sure that I'm not being crowded out by the community, because then I'm going to want to no longer share my resources if I can't use them for my own satellite. And thirdly, we want to make sure that we're able to defend against vulnerabilities due to the ungoverned nature of SatNogs. Right now, SatNogs is very open sourced, and there are admins to enforce the rules, but you can do a lot of things like scheduling absurd numbers of observations in a short period of time, which is analogous to like a DDoS attack, or also there's a risk of other people being able to intercept your uplinks to the spacecraft. All right, so in conclusion, federated ground station networks provide access to diverse station locations and diverse radiocom hardware, along with a number of other benefits, which we discussed. MXL has used SatNogs, which is an FGN, for operating its CubeSats. SatNogs has provided MXL's TBEX mission with some critical advantages, including early identification of a malfunction and some expansion of network capabilities. SatNog's open model prompts some worthwhile questions to consider of the future of FGMs. Here are some individuals and institutions that helped us with this research, and here are our references. That's the end of the presentation. Thank you for listening.